So we now come to example 7, the final example of my series of optimization problems. And the question says, an ordinary soft drink can contains 355 milliliters, that is 355 cubic centimeters, of soda. The can is made of aluminum, and the top of the can is typically about 3 times as thick as the sides and bottom. Determine the dimensions of the most cost-effective can. You may remember that earlier we did a question similar to this, and the only difference was in that case the top was the same thickness as all of the rest of the can. And after we solved the problem, we found that the most efficient shape, the most cost-effective can, would be one where the diameter equaled the height of the can. And we talked in class about how that would make the most sense for that type of can from a cost point of view, but that we don't see very many cans, especially not soft drink cans, that have that actual shape. So we're going to look at it now because we also talked about the fact that a real soda can is quite a lot thicker at the top. And so we're going to redo this problem on the assumption that the can is 3 times as thick at the top as it is everywhere else. So just like before, what we're trying to do here is minimize, well, it says minimize cost, but we all understand that that really comes down to the same thing as minimizing the amount of metal that we use. So I'm going to call it minimize M equals. In the last example, we talked about the area, but this time we have to be a little more clever because we have to recognize that we've got the area of the bottom of the can, which is pi r squared. We've got the area, this lateral area of the side of the can, and that is 2 pi r h. Then we've got the area of the top of the can, which is pi r squared, but we can think of this as being 3 of those pi r squares because it's 3 times as thick. So we think of 3 layers, the same as the bottom. So that's a 3 pi r squared. And so my equation becomes 4 pi r squared plus 2 pi r h. Now, just as we did before, we recognize here that I have a formula in terms of 2 unknowns. The radius and the height are both variables. And we need to come up with a way of connecting those. And we realize that we know that the volume of this can, which is pi r squared h, has to equal 355 cubic centimeters. I can solve this up for h, and I get h is 355 divided by pi r squared. And this now can be substituted in for that h. And so my final formula here becomes m equals 4 pi r squared plus 2 pi r times h, which is now 355 over pi r squared. It would probably make sense for us to try and clean this up as much as we can before we take the derivative. And so I can make this 4 pi r squared. And I recognize here that 2 times 355 is 710. That'll go in the numerator. The pi cancels with that pi. This r cancels one of these r squared r's. And so we're left with m equals 4 pi r squared plus 710 over r. And we're going to need to consider the domain of this equation. And so we say the domain of M is the variable I'm working with here will be R. And R has to be, well, again, if we go back and think of the diagram, we can see that my radius can get smaller and smaller and smaller. It can get vanishingly small. It can get as close to 0 as we want. And by making it very close to 0, as this gets close to 0, the height has to just keep getting longer and longer and longer to accommodate the 355 cubic centimeters. So my minimum radius would be slightly larger than 0. It can get infinitely close to 0. Can't get to 0 because if it was at 0, we wouldn't have a cylinder anymore. And what is my maximum radius? Well, if we ignore the constraints that would probably exist from the machinery that make this thing, mathematically, this radius can get as big as I want it to be, because as the radius keeps getting bigger, the height keeps getting smaller. And since I can make the height arbitrarily small, I can make the radius arbitrarily large. And so, at least mathematically, the radius can extend to infinity. Practically, that wouldn't be the case. But since we don't know anything about the machinery, we just have to do the best we can with the mathematics. Now, we can take the derivative, and I'm going to take the derivative of m with respect to r. And this is going to be 8 pi r here. And the second part is going to be negative 710 over r squared from the Library of Basic Derivatives. And now we do the same thing that we always do. We want to see where does this exist and where does it equal 0. Well, where is it going to exist? The only place we would have a problem would be when r equals 0, and r is not allowed to equal 0 because it's not in my domain. So again, I say dm dr exists for all values of r in our domain. So we don't really have to worry too much about that. Which allows us to start thinking about what happens when our derivative is 0. The derivative is 0 when 8 pi r equals 710 over r squared. Simplifying this, I'm left with r cubed on the left-hand side, and I'm going to get 710 over 8 pi on the right side. And I'm left, therefore, with r equaling the cube root of 710 over 8 pi. I'm not really sure what that is. And again, I'm assuming I don't have a calculator, so I'm going to call that Rm, as in the radius that will minimize the cost of the can. And now I can look at a labeled sign chart. Just like in the last example, I want one vertical bar. I always want two horizontal bars. I'm going to label the vertical bar with my critical value, which in this case is r equals rm. I'm interested in knowing what happens to m prime and m. And I could work out a number for this and try and substitute values in on either side, but I'm going to do the same trick that I've done a number of times, and that is to consider what happens as the radius goes off to the edges of my domain. And I can see as the radius gets closer and closer to 0, the height goes up towards infinity, which is going to use an infinite amount of metal. And likewise, as the radius extends out to infinity, even though the height is smaller, I'm going to still end up using an infinite amount of metal. I'm going to have an infinitely big top and bottom. And so I know that at the extremes, the cost of this, the amount of metal I'm using, is going to infinity. So therefore, I know that the amount of metal as I approach this must be decreasing, and as I move away from it, it must be increasing. I know that it was 0 there, and that tells me that this is a local minimum. I know that the derivatives must have gone this way for that to be true. And I can now justify my answer, and I can say, therefore, m achieves an absolute minimum when the radius is our critical value, r sub m. And that's true because m prime is negative for all r less than our minimum r in my domain. And m prime is greater than 0 for all r greater than rm, again, in the domain. So I ended up with an answer of r equals the cube root of 710 over 8 pi. The question asked me for the dimensions, and so I need to get the height as well. I can go to the next page for that. I already know that r equals the cube root of, 710 over 8 pi. And I can get that h from my previous equation was 355 over pi r squared. And so that's going to be 355 over pi times 710 over 8 pi. If I square that cube root, I end up with this to the 2/3 power. And that would be my final answer. Again, just because I was curious, I ran this into the calculator and I found out that this radius is approximately 3.046 centimeters, that this height is approximately 12.182 centimeters. And interestingly, if you were to go and measure a Coke can, you would discover that those are very close to the actual dimensions of a Coke can.